Sajesh is an assistant professor in the Department of Chemistry, Indian Institute of Technology, Delhi, since 2021. He is leading a research group, Materials and Quantum Crystallography Lab, at IIT Delhi, with a focus on X-ray quantum crystallography to explore chemical bonds and intermolecular interactions towards deriving quantitative insights into crystal engineering of molecular materials, such as flexible crystals, pharmaceutical solids, and piezoelectrics. He completed his PhD at the Indian Institute of Science, Bangalore, in 2014, under the supervision of Professor Guru Rao, where he worked on charge density analysis and crystal engineering studies of pharmaceutical solids. After his PhD, he worked with Mark Spackman at the University of Western Australia, Perth, as a postdoctoral fellow, and with Bo Iversen at Aarhus University, Denmark, as a Marie Curie fellow. Today, Sajesh will present a lecture on chemical applications of X-ray quantum crystallography. Sajesh, screen is yours.
Thank you. Thank you so much, Professor Paulina Dominiak and Professor Christoph Wozniak. So, thank you so much for this invitation and this opportunity to present uh, this lecture under distinguished lectures on quantum crystallography and complementary fields. Today, I will be talking about some chemical applications of X-ray quantum crystallography. Essentially, we study structure and the details of electron density distributions in crystals, the subtle features of chemical bonding, and intermolecular interactions. So our focus is how these are related to how these can be linked to certain material properties. That is our uh, um, dominant theme of our research. And before I enter into this research, my research talk, I should start thanking my students. Um, this is India and Delhi, so we are a lot of people, and these are my research group with both PhD students and master students, as well as some postdocs. We call ourselves as Materials and Quantum Crystallography Lab. I will try to justify this theme of our research, partly at least in this talk. So we have a group of students who focus their research towards quantum crystallography studies, and then more towards crystal engineering of flexible as well as piezoelectric materials and pharmaceutical solids and the formulation. We have this nice team of PhD students, as well as a postdoc, Dr. Amit here, and including master students. So, and sometimes their interests overlap. For example, to understand the flexible behavior of a crystal, we might employ quantum crystallography. Uh, and yeah, these individual disciplines can overlap sometimes, and that's where we think things gets interesting. Now, so with a general theme of applying quantum crystallography into problems within chemistry and crystal engineering, we have been employing the conventional charge density multipolar models, which were referred to as just charge density analysis in the olden days, um, and coupled with these new techniques of Hirschfeld atom refinement or X-ray constrained wave function method, which are a wave function based quantum crystallography, if you can call it that way. Together, by coupling this, combining these techniques along with computational analysis, what we try to do is to understand the intermolecular non-covalent interactions, as well as intramolecular bonds and their electrostatic properties, such as simple properties such as dipole moments to local electric fields, and such features to understand the behavior, such as interesting behavior of materials, such as mechanical flexibility, and in a recently our interest has been also on piezoelectric materials and also pharmaceutical solids. So uh, before I get into the details of quantum crystallography, maybe I'll take a few minutes, um, bit of a flashback when I was a master student, or even just after my undergraduates. One of the questions or one of the confusion I had is this question about orbitals, because when you attend a quantum chemistry lecture, they talk about orbitals as though they are just some abstract mathematical functions. But then you go to your organic chemistry lecture, your professor is going to treat orbitals as these dumbbells and balls, which are physical entities, right? So as a undergraduate student, I was thoroughly confused about it. And one question was, can we really see orbitals or map orbitals? And that is exactly when one of my classmate showed me this paper, which appeared in 1999, and this was the cover page of Nature, which somewhat controversially claimed that orbitals have been observed by um, actually it was a convergent beam electron diffraction experiment on Cu2O, but what they mapped as a d orbital holes, they sort of they were looking somewhat like the dz orbital. This was a very controversial paper. There are so many papers that followed this, and uh, leaving apart those controversy, the essence of this, or what it the way it excited me as a student was, okay, maybe we can map orbitals. This will be a very controversial thing to say, but what everyone would agree is we can map orbital densities, because orbital densities are in real space and we can map them, and that's what we do when we map electron density within crystals. So this we do using including in this study, they used the conventional charge density analysis using multiple formalism. So what we do in conventional crystallography, um, we use just a convolution of this spherical electron density located at individual atomic centers, nuclear positions, and this um, spherical electron density around atoms forms the molecular electron density, which we know is not the case in reality. In reality, in molecules, bonds form, chemical bonds form. There are lone pairs. Basically, there are aspherical features of bonding in molecules and within crystals due to intermolecular interactions and polarization, which are completely ignored in our conventional crystallographic models. And that is where, with the help of multipolar expansion using spherical harmonic functions, charge density multiple modeling helps us to model electron density features, and you can visualize in certain multipolar model. This is what's called as a deformation density map, which is nothing but what you get when you subtract the model density, you subtract it with the spherical atom density. This is what you get, which brings out the features of lone pairs and bonding, as you would expect from a your, after all, your organic chemistry lecturer. He was not uh, lying to you. There are features of density, there are features of orbital density, or orbitals do have real space correspondence, and that's where the chemistry part of it emerges. And for the students who attend this, if you are interested to explore this well-established technique, the Warsaw group is well known for their expertise in this. Uh, so, uh, uh, for a general audience, these are some of those uh, well-known papers which you can follow here. Follow, especially uh, when it comes to the chemical applications of this technique, X-ray charge density analysis to understand chemical bonding and chemistry, and also this textbook by Piero Macchi and Kalogati. So some of my early studies were using this technique of multipolar model to understand intra and intermolecular interactions. What are the nature and origin? Particularly, this is one case of extremely short selenium oxygen interaction, which we published nearly a decade ago, where the selenium oxygen distance was 2.53 angstrom, which is too short if you consider the sum of van der Waals radii of selenium and oxygen, what was called as a chalcogen bonding. So we explored the nature of this interaction and strength of this interaction using this technique. And there are weaker varieties of this chalcogen bonding which seem to which controls this conformation in sulfur containing pharmaceutical drugs. Also, the well-known cases of weak chalcogen interactions, which are ubiquitous in molecular semiconductors, and their nature also could be unraveled using such studies. But in general, the take-home message was, when atoms bond in molecules, the chemical bonding features and the resulting polarization leads to electropositive and electronegative regions, and certain charge depleted regions within atoms, such as electropositive regions, the charge depleted regions, when they electrostatically interact with charge concentrated regions, such as a lone pair density within a oxygen atom, they lead to a very stabilizing interactions in crystals. And some of these interactions, may not be all of them, but many of those interactions can be, the significance can be transferred from not just within crystal packing, but also to biological contexts. I may not get into, some of them are ongoing work or works under revision, so I may not go to those examples. But today I will be focusing on a new variant of quantum crystallography, which is the wave function based quantum crystallography. Uh, so before I get into this, for beginners and those students who are interested in this topic, I have just shown a few papers and chapters of books. This is not an exhaustive list, so if I missed anything, pardon me. But these are some of the papers you can begin with, and some, including some of those historical papers, and some of them from Warsaw itself. So I'm sure uh, students from there, they might be already familiar. And some of Dylan J. Tilaga's initial fundamental work, which showed, the wave functions can be fitted against X-ray diffraction data to, for accurate modeling of electron density. Now, this is a book, chapter by Alessandro Giannoni and Dylan J. Tilaka on in the book edited by Professor Simon Grabowski. So this is also an interesting read. Now, here is a paper where this technique of quantum crystallography is extended to even um, you know large biomolecules such as proteins, using a method called HAR-ELMO, extremely localized molecular orbital technique. I'll not get into the details of this, but this shows the potential of this technique is far-reaching. And at least some part of my today's talk is based on a portion which I've already mentioned in this chapter, with Professor Simon, Alessandro Giannoni, and Dylan J. Tilaga in this textbook, 21st Century Challenges in Chemical Crystallography, in this chapter called The Advent of Quantum Crystallography. So now, if we uh, ask the question, what exactly we mean by quantum crystallography, as the name suggests, of course, It is a marriage of quantum mechanics and crystallography. So if you all have studied this basic relation bit uh, of structure factor and how it is related to the individual atomic scattering factors. For beginners, this is something. Uh, this is a function which tells how much individual atoms within a unit cell scatter. Right. A conventional crystallography uses this particular atomic scattering factor based on it derives this FJs based on spherical atoms. In other words, based on spherical electron density, we derive our atomic scattering factors, which are used in our crystallographic refinement. In the variant called Hirschfeld atom refinement, the quantum crystallographic technique of Hirschfeld atom refinement, what we do is replace this spherical electron density distribution and use aspherical scattering factors. Basically, you use aspherical atoms to define your scattering factors and use those aspherical atomic scattering factors to refine your crystal structure. And where do we get this aspherical atomic scattering factors? That is from wave function. Once you have your conventional crystallographic model, like a normal crystallographic refinement, you got your crystal data, you got your geometry of your molecule. What you can do is you can calculate a wave function, a molecular wave function. It could be a Hartree-Fock level or a DFT wave function. Once you have calculated the wave function, you have molecular electron density, which can be partitioned into atomic pieces. This figure is a bit not bit it's misleading because these are used to represent atomic pieces, but not these are not pieces with specific boundaries like this, but these are pieces where there are no boundaries between themselves, but together they form the molecular density. So this is what's called as fuzzy atoms, atoms where the electron density clouds of individual pieces of aspherical atoms, they sort of merge towards each other. Now we use this in what's called as Hirschfeld atom refinement. Now if you think about it, the conventional crystallography is also sort of quantum crystallography, because the small fj in the equation, the atomic scattering factors, where do they come from? They come from a Hartree-Fock calculation or relativistic level calculation. This is a resolution dependent atomic scattering factors. And this is what we use in a routine crystallographic refinement as well. So in that sense, that's also quantum crystallography. But what makes this apart is we calculate the wave function for this each specific molecule, and we have a tailor-made atomic scattering factors which are aspherical, which we use to refine our structure. So this has been shown to produce very accurate and precise hydrogen atoms, hydrogen atom positions, which are conventionally believed to be not obtainable from X-ray diffraction. Now, so this is an interesting paper in Science Advances 2016. So where they showed that hydrogen atoms can be located accurately and precisely using this technique. Now, these are a few glimpses into some of the applications of these techniques. Where in a recent study, my student Atul employed this to locate the proton position in multi-component crystals. These are called salt, co-crystal, and the continuum between them. So when there is a proton with an acid, when it interacts with the base, if the proton is transferred, of course, we call it a salt. But how do you know whether it's a salt or co-crystal? Yes, in many cases, its conventional technique is sufficient, but there are cases where it's not clear whether it's a salt or co-crystal. Such cases, we have employed this, and we also compared it with the nitrogen 1s binding energies from X-ray photoelectron spectroscopy, and which correlate well with our assumption of salt or co-crystal, or an intermediate state which we call as a continuum structure. This is another case where uh, Ashish Singh, my PhD student Ashish Singh, employed this technique to study weak interactions involving thiols. Thiols is such a common, they are such a common functional group, but the entire Cambridge structured database contains uh, only two thiol SH bond lengths from neutron diffraction, and most of the other SH bond lengths were quite far from the neutron diffraction values, and many of them are really wrong. So we thought this would be interest. It would be really interesting to look at this thiols and their intermolecular interactions, and this is an ongoing work, and the manuscript is under preparation. And we also complemented this with neutron diffraction study, and also analyzed the very weak subtle interactions involving thiol functional group. And in another chemical application of this quantum crystallography, uh, where uh, my student Srijan studied using high resolution data the electrostatic moments uh, of basically starting with the dipole moment of piezoelectric molecular crystals, and also he obtained the spontaneous polarization in a series of molecular piezoelectrics. Our next speaker is going to talk about piezoelectrics in detail. So this is just a teaser to that. So we looked at how accurately we can look at the dipole moment values. Are they it's an ongoing study, but are they any different from a simple single point calculations that you do from a conventional crystallographic model? Then here is another application of the same from a independent atom model. If you calculate a wave function, you get a dipole moment of around 6.3 dBi, whereas our quantum crystallographic model showed the enhancement due to the crystal field effect in this flexible crystal, elastically flexible crystal, which also showed when you elastically bend it in the bend region, it shows a systematic tuning of fluorescence lifetime and also the band gap within the material. So this is something we recently published, and some other applications into interesting materials, applications of this quantum crystallographic technique. Uh, Mainly, it was in our group. We use this technique to study flexible crystals and the structural origin to get more accurate information about the different intermolecular interaction motifs which may be responsible for holding the structural integrity of the crystals while they are bending. So one such motif we recently identified. This is again a manuscript under preparation or just ready to submit, where we identified this cyano groups, this nitrile nitrile interaction motif, which might you might think that it's formed by a very weak CHN hydrogen bond, but there is this anti-parallel orientation of the cyano groups, which forms a strong electrostatic, dipole-dipole type interaction, which makes it a strong motif and which plays a role in the mechanical property in a series of molecular crystals which we identified. And since it is a, I'll not get into the details of this, but you can see how we can use this technique to unravel the electron density distribution in such scenarios. So these are the crystals that are elastically bending, plastically bending, and in some case this is what's called as ferroelasticity. And the same motif was also found to be important structural feature in some of the examples discovered by my student Ravi Teja, and this is also again an ongoing work. We use this technique in recently in a, this is, I cannot say it's a particularly significant application, but when you want to get more accurate interaction energies, um, you need more accurate structure and hydrogen bond positions, and particularly in questions like when you compare the relative stabilities of polymorphs, for example, those small difference in hydrogen positions add up to big difference or significant difference in their lattice cohesive energies. Now, if we enter to the next level of quantum crystallographic refinement. We not only refine hydrogen atom positions or their atomic displacement parameters, but what's called as X-ray wave function refinement or X-ray constraint refinement, or this name is under debate now. There's a debate going on whether we should call it X-ray regulated uh, um, wave function or X-ray restrained wave function, whatever you call it. What we try to do in this technique is, once you get the most accurate geometry from our Hirschfeld atom refinement, the first method that we discussed, you calculate a wave function, but then you start adjusting your wave function, tuning your molecular orbital coefficients, adjust your orbital coefficients, or the coefficients of the basis functions you use to represent your molecular orbitals, such that your net electron density fits best with your X-ray data. And it also has a variational part where you try to minimize the energy of the wave function. And this technique has uh, a few advantages over conventional multipolar method, where there is no energy component and your fitting can be really affected by a few bad reflections in your X-ray data set. So not only that, what you get at the end of this fitting procedure is a wave function for your molecule in a crystal, where the density is electron density and the wave function itself is fitted against, in a sense, fitted against your X-ray data, experimental data. In that sense, in a very loose sense, you may call them as experimental wave functions, but I'm sure there will be people who have strong disagreement uh, in calling them as experimental wave functions. Irrespective of what you call them, once you have a fitted wave function which has the crystal field polarization effects and the true bonding effects, this wave function can be used for an in-depth analysis of chemical bonding and other properties, analysis of other properties. So one such, I'll briefly showcase a few cases where we have applied this technique of X-ray constrained wave function. One such example is the initial case, the first case I discussed of a selenium oxygen, the chalcogen bonding. That was about the intermolecular selenium oxygen bonding. Whereas if you look at the molecule itself, this is an antioxidant. It's a organoselenium antioxidant. This particular selenium nitrogen bond was of particular importance, and we wanted to study the nature of that bond using this X-ray constraint wave function. And when we plotted this electron density maps, I'll get into that in a minute. But when you compare the electron density at different bond critical points, different chemical bonds within this molecule, uh, the fitted versus unfitted wave function, if you compare, the density sort of match very well. But you can see the Laplacian, the the curvature of density in space, that is not fitting very well, matching not so well, as you can see here. And this is for the another analog, which is a sort of a pyridine analog, as you can see here, below here. And here as well, you can see the Laplacian doesn't agree very well with between the fitted and unfitted wave function. What it tells us is, yes, the fitting procedure does change the electron density distribution, which may not be immediately visible in some cases in the density itself, but the Laplacian brings out such changes due to fitting. And the deformation density distribution within this molecular plane clearly brings out this difference. Here you can see around selenium, and this is the selenium nitrogen bond. You see the bonding density is very less compared to other bonds. You can see here, means it's essentially a very weak bond with not much of a shared electron density between that bond. And um, okay, I'll not get into those details of intermolecular interactions, but we can also see the features of what's called as a sigma hole. which is a charge depleted region along the selenium nitrogen bond. You can clearly see this here, and that is what is leading to the intermolecular selenium chalcogen bonding interaction. Now that we have a wave function that is fitted with the experimental data, we can also use it to quantify the percentage ionicity and covalency associated with the different bonds. And what we see here is this particular bond has a certain degree of ionicity, as you can see from the electron density distribution here, which implied this peculiar nature of these bonds. And when we did a TDDFT optimization of this structure, what happened is in the excited state, this particular selenium nitrogen bond was found to be cleaving. The bond breaks in the excited state, which further implied that the selenium nitrogen bond in this molecule could indeed be a dynamic bond, as indicated by our bonding analysis from X-ray wave function. So this work we recently published in Chemistry European Journal, and we have reasons to believe that this is which cleaves with a photo excitation. So this can be called as a dynamic covalent bond, and such covalent bonds, not selenium nitrogen but diselenide and ditelluride bond, were also found to be playing a role in this beautiful phenomenon of thermochromism in diphenyl diselenide and ditelluride crystals, where without any phase transition or tautomerization or any significant change in molecular conformation, these crystals were found to be changing their color. And I will not be able to get into the details of this work. It's a bit tricky and confusing because there are multiple factors which are intermolecular chalcogen bonds and intramolecular diselenide and ditelluride bonds, which plays a partial role, at least as per our understanding, and that's what we conjectured in this paper, and that seemed to be uh, playing a role in the in this thermochromic phenomenon in these crystals. So another quick glimpse into another ongoing work in our group is that of this ruthenium complex, where our textbook type 18 electron rule implies that maybe there is a ruthenium metal metal bond in order to obey 18 electron rule. But yeah, all such complexes don't have to obey 18 electron rule, but we were curious to see whether there is a ruthenium bond or not. So we collected high resolution data, 0.45 angstrom resolution data on this complex, and we model both HAR as well as X-ray constraint wave function on this structure, and we analyze the bonding features. And one good thing is we could also do using singlet and triplet wave functions, the unrestricted calculations, which showed sort of uh, notable differences in the not huge but noticeable differences in the fitting parameters and residual densities, which prompts us to think whether we can use these X-ray constraint models. Can they inform us about the spin state between if you want to see whether a given molecule is in triplet or singlet state, or an interesting scenario with the single molecule magnets? um, Maybe we should be able to extend, and our current efforts are in that direction, to extract information related to spin states within molecules. um, and coming back to our initial discussion on the ruthenium bonding, we could not find any ruthenium bond path in this structure, which was confirmed by its bonding analysis. And these I will skip the details of bonding in this structure. So this is an ongoing study. Now, before I stop, maybe a quick glimpse into a recent study, which is again another ongoing study. This is based on a recent paper by Ishigaki et al., which appeared in Nature just a couple of months ago, where they reported a carbon-carbon one electron sigma bond. So we were interested or curious to know the nature of this bond. Um, what is the electron density distribution between the carbon atoms there. So this is that paper where they claim that it is a direct evidence for a carbon-carbon one electron sigma bond, and they had the crystal structure, and the main evidence they produce for this particular bond between two such carbon atoms, which are a bit far apart, not very close, 2.92 angstrom, was the calculated force constant of around 50 nanometer inverse, and CC stretching frequency of around 379 centimeter inverse, which was confirmed by experimental Raman spectra. And this was the report. So we model QCR model. We from our electron density model, we analyze the uh, um, bond path between two carbon atoms, which are supposedly bound by this CC carbon-carbon one electron sigma bond. And what we could find is a very low value of electron density as well as Laplacian here, which are typically comparable to those of a hydrogen bond or intermolecular interactions. Then we also got other examples of such one electron bonds from the literature and got the structure factor, uh, got the X-ray data, deposited X-ray data, and did modeling. And these are the values for boron-boron such bonding, and copper aluminum and copper gallium bonding, which was reported in the literature. So this is an ongoing work. Our question was, is it half a bond or just a weak interaction similar to pi-pi, where an electron is just trapped between two carbons in close proximity? So this is an ongoing work, but such interesting questions about bonding and non-covalent interactions can be explored, and X-ray quantum crystallography is indeed a very effective tool to answer such questions. And we are currently also interested to use quantum crystallography in exploring properties, material properties such as this, and piezoelectricity, as well as flexibility, and um, other. I think rest of the things I will not repeat or summarize. With that, I thank again Professor Paulina Domniak and Professor Christoph Wozniak for this kind invitation, and all my PhD students and past and present master students, as well as postdocs and collaborators within our Indian Institute of Technology, as well as foreign collaborators. And before I stop, I just want to advertise this uh, special issue that we are guest editing, Professor Simon Grabowski and Professor Bo Iverson and myself. This is to celebrate the 70th birthday of Professor Mark Spackman. If you're, so you're all, uh, welcome to submit your articles to this particular special issue. So with that, I'll stop.
Thank you very much, Sajesh, for this beautiful lecture. I'm really impressed by the number and quality of your collaborators from all over the world, but particularly domestic ones. I think you are excellent example how the field is intensively growing in India, and really it's beautiful to see the strengthening, the fact that in quite a few places there is such a big community working in this field. So we have several questions. The first one comes from from Vikas. Through what mechanism are we getting thermochromism? Why these crystals are colored? Why not colorless?
Okay, that is a very okay, Vikas. Uh, the mechanism we still don't fully establish, but the mechanism, the way we relate this to the charge shift bonding is uh, the charge shift bond. If you are not familiar, it is proposed. The theoretical model is, some people have opposition against this model, but I would explain the model is, it's a resonance structure between two ionic bonds. So imagine the two selenium atoms. One is positive, another is negative, and it forms ionic bond. But imagine them to be fluctuating in a quantum mechanical sense, fluctuate like a resonance structure. So what we have proposed in this paper is uh, the temperature, the subtle changes, not subtle, it's from 100 Kelvin to 293 Kelvin. The temperature difference makes, it affects these electronic states. You can say it should be related to the sort of a vibronic coupling effect happening there. So it's essentially, we pinpointed it is to the just the only the vibrational modes uh, that are mainly playing a role. Number one. Number two, we may not be seeing, we may be underestimating the conformational change in this molecule when we look at the average crystallographic positions. So we did also neutron diffraction data. We also quantified the amplitude of those vibrations, which takes the torsional angles to a higher torsional angle difference, and we calculated the changes in electronic states, and we quantified what will be the HOMO to LUMO change if you just calculate from a static crystal structure, but also by calculating the range of amplitude allowed by a higher vibrational motion. So what we have, we still don't have clarity, but I would say what happens, what it is to do with the dynamic bond is, it is being shown in just the analog structure of this diselenate that these bonds can cleave upon photoexcitation. So uh, it's a combination of a highly labile charge shift bonding situation, which coupled with the vibronic states that might be leading to this color change. That is it's like a conjecture and a vague hypothesis, but that's all we have. Otherwise, we don't have any clear mechanism as why it's color changing. This is the best we could come, and that's what we have mentioned in the paper also. But it's a open question for somebody like for a something like a excited state spectroscopy could tell probably, but that's all we have mentioned in the paper also. So Vikas, so I don't have a clear answer to give you yet. So yes, the homolomo gap changes, and the change we estimate from a variable temperature XRD is not sufficient to explain this color change. Or even if you calculate the band structure also, you will not see any significant color change. But it's a vibronic phenomenon. That's what we suspect. Sorry if I'm not very clear in this.
Okay, we have yet another question coming from Biswait Moanty. In your, sorry if I pronounce this wrongly, in your TD DFT calculations, you mentioned bond dissociation. Could you clarify which excited state the bond breaks?
It's the first one.
How the electronic transitions influence the bond dissociation process?
Okay, it's to the LUMO, one electron transition, and how it happens is when you do a TDDFT optimization in the normal, it's a simple Gaussian calculation that we performed, which only allows the transition, which only includes the transition to the first excitation state, which changed the geometry, and on the change geometry we did the other calculation. But we don't have to do any calculation. Even we can see the geometry itself is twisting, the molecule is twisting, and the bond distance is clearly apart. So we don't even need an electron density analysis to see this bond cleavage in the excited state.
Mm-hmm.
Yeah,
And
it is the default excited state calculation in any quantum chemical package, which is to the LUMO. Yeah.
The next one comes from Hans-Bert Birgi, from Professor Hans-Bert Birgi. To what extent do weak interactions depend on the wider environment of the weakly interacting atoms? Example, selenium, nitrogen, or carbon-carbon.
Okay, if I understand the question correctly, is to what extent such bonding is influenced by weak interaction? Is that the question?
Maybe the other way around. To what extent do weak interactions depend on the wider environment?
Okay, I think, okay, if I assume the question is some of these interactions which we tend to be assigning a specific interaction could be effect of overall crystal packing, not just those specific atom-atom contact, right? Okay, I get that. So, but yes, there are many such cases in the literature where people just go by pure geometric arguments to call specific interactions and call them stabilizing if there is a net negative interaction energy. But this is not such a case. We are confident because if you look at the sum of van der Waals radii, it is 2.53 angstrom. The sum of van der Waals sum of van der Waals radii is around 3.4 angstrom for selenium and oxygen, but the observed distance is 2.53 angstrom. That is too short to be an accident. And not only that, the sigma hole geometry, maybe I should share the screen. So this selenium nitrogen, when the oxygen attacks from this direction, that oxygen selenium nitrogen, that particular angle is always very close to linear, as it is in case of hydrogen bonds. So plus we have evidence from the electron density distribution as well, the electrostatic complementarity. So it's a electrostatically driven short contact which are strong enough. If I remember, the interaction energies were comparable to that of hydrogen bonds. In this case, hydrogen bonds, classical hydrogen bonds. So I hope that answers the question.
The next one is defined by Piero. In routine dimer, you tested singlet and triplet state with a minor preference for the triplet. Slightly better R factors. Is this difference significant, taking into account that the triplet calculation is inherently using more parameters? Is the complex known for the paramagnetism?
No, we also believe in this case it's not such a big question. It's we believe it is actually a singlet. It was not such a very curious case, but it is, and also the difference in residuals and R factors are. I agree with the Professor Piero Macchi's observation, but we take it as an indication to extend this study. Maybe where we have a real chemical question such as this. In this case, I agree the difference is very small and subtle, maybe not sufficient to confirm that. But we are currently studying more a series of cases where we test this idea. But if the distribution of in the triplet and singlet distribution of density, if it's sufficiently different, my expectation is that it will reflect in the fitting parameters. And if that is the case, it will be XCW will have the potential in exploring such systems. But in the current example I showed, it was only a subtle difference. I agree. Yeah, and it's an ongoing work, and also even the level of theory and all we used is not optimum. It's only an initial result. Yes.
Okay, and
It's yeah.
so the next questions will be asked by Yasser. Yasser, please.
Thank you so much, Professor Wojnak and Professor Domeniak and Professor Tomasz for your talk. I'm asking a question about the piezoelectric property because I don't know the detail of your work. Because this property some kind of related also to the symmetry of the crystal, to the space group. So if your space group is center symmetric, despite any kind of bonding, you cannot have this property. So how, for example, you could, let's say, make the link between piezoelectric property and chemical bonding, or what are the criteria that you used? Thank you.
Okay. Okay. We made an attempt recently to make a link between the molecular level properties and the observed piezoelectric coefficients. That is a paper under review, but that's not using quantum crystallography. It is a complex phenomenon, and I'm sure Professor Sarah Gaurin would be able to shed some light into that. But from our study, what we see is we start with simple properties such as dipole moment and the vector sum of molecular dipole moment per unit cell volume, which we call as the spontaneous polarization. That is one of the parameters we analyzed. We also analyzed how tightly or loosely these molecules are bound, because it's essentially an electromechanical coupling phenomenon. So we defined a crystal packing index using a simple percentage difference between the van der Waals volume and Hirschfeld surface volume, the percentage difference. We defined a simple close packing index. One thing we observed is when the molecules, if they are loosely packed, naturally with an applied stress, they can better reorient and show, so there was no direct correlation with any of the parameters we analyzed. But when we took cases where all other parameters are at least comparable, then we can see with a higher dipole moment, higher is the piezoelectric response. But we have in molecular crystals, we have only not so many examples. I'm sure Sarah would be able to add to this. But as of now, structure property correlation, direct correlation efforts are limited by the limited number of examples we have in molecular piezoelectrics. So what we try to do is, what is the dipole moment? And especially, as you said, they all crystallize in non-centrosymmetric space groups, and many of them in polar space groups. How those crystal field effects further enhance these dipole moments of these molecules. That is the only part we looked at in this particular work.
It's perfect. Thank you so much.
Thank you. And then we have a discussion starting with Reza Kia question. But I think that the oxidation state of ruthenium in that complex is free, and it's paramagnetic. And the answer of Professor Hans Bedbirgi, a given type of weak interactions. No, that's not related to this. Then we have Piero's comment, but I think that that not if there is a ruthenium bond, which was the question of the study, and Teresa, thanks for this. What is your comment on this?
Okay, my comment is it's not ruthenium 3+, it is 2+. We have 2 ruthenium and 2 neutral cymene ligand, and 1 chlorine, like a terminal chlorine, and 1 chlorine which is bridging, and 1 hydride. So we have 4 negative charges from the ligand and 2 ruthenium. So it is ruthenium 2+. in our case.
Mhm.
And it's not necessary that all such material complexes have to obey 18 electron rule, but if it is to obey, then we were expecting a single bond between them, and we could not see that.
Mhm.
Well, I
Yes.
read what I wrote. If you look at the given type of weak interactions, for example, your selenium-nitrogen interaction, if you look at the type of such interaction, usually this type shows a wide range of geometries. That is, they must be influenced by the wider environment. So that was my question. What is the influence of the wider environment on any given weak interaction like the one you were discussing?
Okay, when you say the wider environment is how much other interactions influence or perturb the directional preferences or geometries of this one, if that is your question, at least the
Go,
system.
go, go, go to the CST, Sajesh, and look for all selenium nitrogen interactions.
The
And you find a lot of them.
yes,
Some of them, and they cover a range of geometries. Usually, they are orientationally, they have an orientational character, but they cover a wide range. So they
yes,
depend on the wider environment, not just on the selenium and nitrogen or the two weakly interacting atoms.
we have done such a wide CSD analysis, chemical structural database analysis, and there is a clear and obvious preference for this N2 sigma star directionality, linearity of oxygen, selenium, and nitrogen. So may not be 180-degree, but within, just like in hydrogen bonds. If you think, and even more than hydrogen bonds, if
What
you
about the selenium nitrogen distance?
selenium nitrogen distance, that I have to.
Yeah, they will vary.
Oh, yeah. Okay, good that you asked this question. In fact, uh, um, the Australian group, Stephen Mogak, they with Professor White, they exactly studied this particular chalcogen bonded system, selenium oxygen, very recently, and they can see that with the selenium oxygen, if I remember correctly, the selenium oxygen intermolecular interaction, when it becomes shorter, they could see a slight elongation of the selenium nitrogen intramolecular bond, which is further, and in theory we are obviously seeing it, but experimentally, if I remember, I think it was above error limit of bond lengths, but I have to cross check. I'm telling this from the memory of listening to a talk in the last IUCR in Melbourne. So, um, so if your question is about the directionality, I don't think it is an accident, and just the analogous uh, sulfur-containing interactions, which are much weaker, even they are very directional. And in a follow-up paper, I have discussed this. I can show you. I did not discuss, but I just showed the. In this particular paper, we looked at such sulfur oxygen contacts, and we not only looked at some uh, single component, we looked at a number of multi-component structures where we could also show see this directionality with respect to that sigma bond. So they prefer to always interact along the direction of that sigma bond containing selenium. When it comes to sulfur, of course, it will not be as strong a directionality as a selenium, but selenium chalcogen bond has a
I'm
packing
not,
directly
I'm
involved.
not, I'm not questioning the directionality, but okay, let's keep it at that. Thank you very much, Sajesh.
Oh, thank you.
Okay, so yeah, yeah.
And there is the last is rather a comment, is agreement that by Reza Kia that by ruthenium bond it will be diamagnetic.
Okay.
I do not see. Are there any new questions or comments? If not, let us thank Sajesh for this discussion and for the lecture.